This is Tom Rowlands-Rees, and you're listening to Switched On, the podcast brought to you by BloombergNEF. As AI drives a new wave of data center expansion, attention is shifting to the supply chains that deliver the physical infrastructure behind them. Higher density computing is pushing new demands across equipment markets, from transformers and switchgear to advanced cooling systems and on-site energy storage, straining supply chains that were never designed for this speed or scale. Manufacturers, developers, and utilities are now reworking how data center projects are designed, sourced, and built to keep pace with demand. So, how are data center supply chains evolving, and where are the biggest constraints and opportunities emerging? On today's show, we bring you a discussion on data center supply chain innovation from the BNEF Summit San Francisco, where Mark Daly, BNEF's Head of Technology and Innovation, spoke with Steve Carlini, Chief Advocate for Data Centers and the AI Energy Management Business Unit at Schneider Electric, Haroon Inam, the co-founder and chief executive officer of DG Matrix, Jill Macari, the chief financial officer of VEIR, and Angela Taylor, the chief of staff and head of strategy at LiquidStack. BNEF summits bring together experts from across finance, energy, and technology to share insights, build connections, and explore how innovations in clean energy technologies are reshaping global markets. Held in cities around the world, they offer the ideas and perspective needed to navigate the transition to a cleaner future. If you'd like to join us at an upcoming event, including the BNEF Summit Beijing on March 12th, head to bnef.com and click on Events, where you can also watch highlights and videos from past summits. And now to Mark's panel from the BNEF Summit San Francisco titled Seeing Beyond the Chips, Innovations in Data Center Supply Chains.
We ended that last panel with actually Raj, in case anyone wasn't here, Raj from Aligned Data Centers kind of said, oh, well, we're developing these shells that you can plug servers into, and really that's the outlet, and what's changing is the server. But there's actually a little bit more nuance to it than that, and he's kind of perfectly set us up for this panel, which is really about how the power outlet and all the other ancillary equipment in a data center is changing, because obviously when there's so much capital going into a business like this, there's always opportunity for improving the efficiency and the types of products that go into it. So thank you very much to everyone for joining me here today. So let's start with you, Angela. If you read about data centers and kind of what's changing in data centers right now, one of the, forgive me, hot topics is how the chips are actually cooled. And this phrase, liquid cooling, is what you see in all the headlines now. So can you give us a bit of a primer on what exactly that means and how it's different than what came before?
Yeah, sure, happy to. So liquid cooling is, as it sounds, it is cooling the compute within the rack using liquid versus air, which is traditionally how it's been done in the data center. And they're doing it for a number of reasons. Liquid has higher cooling capacity, it has higher thermal conductivity. So the reason that you're hearing a lot about it is because as we start to deploy racks that are more dense, moving from 40 kilowatts a rack up to 140 right now, next 800, then perhaps 1 megawatt, you really, the physics and just economics of air no longer exist. So yeah, liquid cooling is here.
Yeah, great. And just to kind of clarify, it's like when you talk about a rack, it's kind of that big metal shelf where it used to be a HPE server, and now it's an Nvidia GPU that costs millions of dollars.
Exactly.
So oftentimes, something that I'm asked by my friends is, liquid cooling, it's, I'm kind of worried about the water consumption of data centers. Is this going to make it worse? Is AI just making data centers even more water hungry?
It depends. No. So you have to separate, when you think about data centers, you have to separate legacy data centers and AI data centers.
Yeah.
So when you think about water consumption of an AI data center, it can be very minimal, because when you implement liquid cooling, especially if it's a completely liquid cooled environment, over air you can save somewhere between 30 to 50% in energy, and you can save 30 to 80% in water, not energy. So yeah, in the water side of it, you do have some substantial savings that you can realize with liquid cooling. Again, it's going to be a foundational technology for the AI side of it. So I think your opportunity here is, can we implement it in the non-AI side, in which case you would start to see substantial savings in the water side.
And is that kind of like one of the questions for you as a product development officer? Like, are you thinking about how do I expand this to more types of data centers?
Well, you have to have the need, right?
Yeah.
There's lots of legacy infrastructure that exists there, so there has to be some motivation to move into that direction. And yeah, of course, we do think about that. And now that data centers will have more familiarity with liquid cooling, then perhaps the barrier to entry becomes a little lower.
And then on the energy efficiency, you kind of mentioned that. Is it a positive, negative? How does liquid cooling impact that?
Yeah, it depends on such an engineering answer. It depends. It depends on the type of liquid cooling that you are implementing. So there are 4 sort of generally accepted types of liquid cooling. You have 2 methods, direct-to-chip and immersion, and within each of those you have single phase and 2-phase. And that the phase just is the liquid phase throughout the solution. So when you're thinking about energy in a direct-to-chip solution right now, what's happening is you have a cold plate on the hottest components within the board, the compute board, and they're circulating water and picking up that heat and dispersing it in other parts of the system. But you're only really cooling 70%. So it's not on everything, right? And you still need a fan in order to be able to cool the other parts of it and then pumping around. So that's a little less energy efficient, but still more energy efficient than air. In immersion, you are dunking it in a dielectric fluid, and that has much greater potential for energy savings.
Okay. Yeah. Steven, can you talk a little bit about the trade-offs between this kind of immersion versus direct-to-chip? Schneider's active in the cooling space for data centers.
Yeah, liquid cooling is not new. It's been around now for computing over 60 years. So it's not something that, all of a sudden has become mainstream because, it uses less water or it's more efficient. It's become mainstream because it's impossible to cool the new GPUs without liquid cooling. But we've, through our acquisitions, some of the companies that we used to do Cray supercomputers back in 2018 at 400 kilowatts per rack. So this new high density and the challenges, as Angela said, liquid cooling is an architecture, and if you architect it right, it could use minimal use of water. It may use a little bit more electricity at that point, but it will use much less water. The different types of cooling that are available today, it depends on who the data center operator is. All of the new data centers that are deploying the Blackwell Ultras and now the Vera Rubins, they are all being built from scratch. Yeah. And they are going to use direct-to-chip liquid cooling. Some of the older data centers, it's very, 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 very tough and expensive to overhaul a 10 kilowatt per rack data center into a 140 kilowatt per rack data center. So what a lot of those data centers are doing some other types of technologies that some people call liquid cooling, some don't, like rear door heat exchangers. With rear door heat exchangers, you could bolt them onto the back of the rack, you could use your existing chilling technology, and you could get 75 kilowatts per rack. So that's much, much less disruptive. But as Angela was saying, we're at 140 kilowatts. In 6 months, there'll be 200 kilowatts, and then before you know it, we're back to 400, 600 kilowatts per rack.
Yeah.
Okay, great. You mentioned actually that Schneider made some acquisitions in the space. I think that's very much a theme we've seen in the heating and cooling space more broadly in the economy. There's been a lot of heat pump acquisitions, but specifically relating to data centers, there's been a lot of activity. So Schneider.
Yeah. Schneider made an acquisition. We again had a long history of cooling. We needed more of a portfolio. We needed more production capacity. We just, when the Blackstone guy said, "Oh, it's $7 trillion," this number seems small. We just signed a contract with Switch Data Centers, $1.9 billion for chillers, for liquid cooling, for data centers. So, that's an incredible incredible number just for cooling. But one of our competitors who is not yet very, very strong in power, but not in cooling, which is Eaton Corporation, and they just spent over $9 billion on Boyd. So it's a company that's very close to my house in Florida. By the way, they're my neighbor. But that's a huge $9 billion acquisition for mainly for a liquid cooling company.
So there's a lot of electrical companies kind of building this full value stack of equipment across. Yeah, okay, so kind of a bit more vertical integration. So using that to kind of spin off into having a bit more of a conversation about electrical equipment and the innovations that are happening there. Jill, can you talk us through, you've explained what VEIR does.
Yes.
Can you explain how, I mean, it didn't start out as a data center electrical company, and that's not just what you do now, but how has it gotten from where it's founded to where it is now?
Yeah, so VEIR was actually founded to solve all the power density problems that exist actually at the high voltage level in transmission and distribution, and really using evaporative liquid nitrogen cooling technology combined with superconducting, which has been around for 25 plus years in lots of different grid-connected projects, but really what we've found is an opportunity to take that idea and commercialize low voltage and medium voltage products to help solve some of the behind-the-meter challenges that we see in data centers today. And for us, that really means on the medium voltage side, helping to move power around the data center campus. So this is from the substation into the buildings, and really this is otherwise done through copper cables and a huge amount of cement and labor. Our products actually reduce that labor and cement cost by about 40%. Inside the building, we're actually able to offer a different alternative to traditional bus bar, copper bus bar solutions, and we are able to move about 10x the power with the same space. So that offers more weight savings, space savings, and performance savings as GPUs require increased proximity to one another to really maximize that performance.
Yeah, I mean, I've heard some really funny statistics about, like, if you want to power like a 1 megawatt GPU rack with a copper cable, it's something like that thick, and then you have to just reinforce it so much. So there's a lot of engineering challenges associated with this.
And the heat.
And the heat, yeah. Haroon, walk us through. You said a lot of words when you introduced your product. Can you explain what exactly it is that it does, and again, how it relates to this data center conversation?
So our technology basically can take any AC or DC source of power, multiple ones at the same time, and aggregate them using a solid state transformer that's heavily patented by us. Nobody else has this technology. And what we can do is that we can add, for example, solar or fuel cell or batteries or natural gas gensets or the grid. And we can add them in any ratio we want down to the millionth of a second. And we balance the power in order to extract the best transients from the best transient source. Otherwise, we lower the cost of the energy that we transfer, and we look for the highest efficiency. So we have our own energy management system to optimize this. And simultaneously, we can deliver multiple sources of power to multiple megawatts of Nvidia 800 volt racks for the Gen AI servers. That's our technology. So it's consolidating 11 to 17 different pieces of equipment into one piece of equipment.
And am I right in describing it as like it's kind of the entry point from the grid to the data center, and now everything's just being put in?
Yeah, for entry point from the grid to the data center, but also for all these other energy sources. Yeah. The way it's done today in a legacy system is you have a number of transformers, rectifiers, inverters, maximum power point tracking, fuel cell, DC to DC converters. We eliminate all of that, and we take raw sources of energy into our multi-port solid-state transformer, each port devoted to one source and one load, and then we provide consolidated output power. We clean up the harmonics, we clean up the surges. So,
yeah.
I mean, it took us 600,000 engineering hours to deliver the first pilot, so it wasn't an easy thing to go through.
Yeah. And I mean, you didn't start as a data center company either. This was something that was built for general grid applications, right?
We actually started for fleet charging originally because fleets couldn't get enough power. And when we put our first pilot in the ground to show what we could do, we got a call from one of these GPU companies and said, is this real? We go, absolutely. And then they started giving us specs and helping us out. And that's how we got to where we are. We're looking at a massive pipeline over the next 2-3 years as we start delivering product this year.
I'm actually kind of interested because like neither of the companies were founded with this in mind, but how much effort would you say you spend now on your kind of utility customers and your grid projects versus like what's going into data centers? Can you share anything about that?
Sure. I think utilities are a conservative market. It takes time to break into utilities. It's a massive market, but it's going to take time. The commercial and industrial market is where we started deliberately in order to overcome those issues.
Okay.
And then the data centers came along, which was quite frankly just pure luck. We were there at the right time, and they need power, and they need it now.
Okay, Jill.
Yeah, similarly, we have lots of utility customers that we continue to have conversations with, but really we have the opportunity to show how superconducting works and how it solves a lot of the medium voltage challenges that many of the utilities face. But we get to do that sort of with the data center customers, build that traction, and then scale it to utilities.
Okay, great. And a question like I think everyone always asks a lot about data centers because it had a huge influence historically was that people thought the power demand was going to blow up since like 2008, and it never really did because things always got more and more efficient. So on the electrical equipment side, like innovations are focused on getting the power into a smaller form factor, making it cleaner. Are they impacting efficiency on a meaningful level?
I think, well, first of all, it's a radical change when you go from a 6 kilowatt rack or an 8 kilowatt rack to a megawatt class rack, right? Yeah. And that's where we're headed by 2027, early to middle of 27. That's a 100x increase. So you cannot possibly have big, thick, long runs of copper that are going to carry 100 times more current. You've got to rethink it out. In addition, if data centers have a real problem in getting power to the facility, it isn't about efficiency as much as it is about stranded power. Power that's designed in legacy architectures that leaves 10, 20%, 30% of power that can't be delivered to the chip. So our focus is on eliminating that stranded power. Why? Well, let's take a 100 megawatt data center. Let's say it's just 15%. That's 15 megawatts. 15 megawatts will generate $150 million of AI revenue a year. It's not efficiency. It's about eliminating stranded power under all sorts of failure modes and the right architecture to blend those sources and deliver it. And that's what we're absolutely laser focused on. But efficiency, sorry if I could, also matters because when you aggregate all this equipment into a small footprint, you lose less copper, you have far less losses. So you gain a few percentage points. But the stranded power is where the real money is.
I would just also add, I agree with everything you've said. I would also just add, what we hear a lot from our customers is about speed to power. So this is about those greenfield projects that Steven was referring to, how quickly can they get built? And so for us, this is really about helping to solve that challenge by eliminating some of the labor costs and some of the cement costs and some of the install time, really through a more simplified system. And in our case, it's just digging less trenches.
Yeah, sometimes innovation really is that simple.
Yeah.
Cool. So I didn't really mention this in the intro, but it's kind of become apparent throughout the conversation that so much of what's going on at all of your companies is really defined by what's happening in another company, Nvidia, and the fact that they've fundamentally redesigned what's going into data centers and what data centers can even be used for. But they kind of have a funny influence because then a lot of the sector is kind of designing around what they use. And an interesting story maybe some people in the audience saw, Jensen Huang, the CEO of Nvidia, was at a conference recently and kind of spoke about the fact that the new GPU, the VEIR Rubin, is going to be running so hot that you can use entirely liquid cooling and actually you won't need to use chillers at all. So that 1.9 billion order, Steven, you were talking about. Yeah. Do you think that this is realistic? Do you think, what's the kind of relationship between how you develop your equipment on the cooling side and what NVIDIA is saying on that front?
Yeah, so I spent all morning with NVIDIA, And today, yes.
Okay.
And we actually spent an hour on this specific subject because we were preparing kind of I would call it a position paper on exactly what Jensen meant. Because he really didn't mean that anyone was going to run their data centers without chillers. What he meant was it's possible at 40 degrees C in certain climates that they could possibly run part of the time, without mechanical chillers. But that's really not how it came across. And Nvidia had a lot of negative reactions from a lot of their cooling suppliers. But we were not as, I guess, aggressive. So what happened was things calmed down, and they decided not to issue this paper. But the reality is nobody is going to run their data centers at 45 degrees Celsius because you don't know how long the chips are going to last, and you don't know if they're going to overheat and you're going to lose control and not have functionality. So most of our customers, and this happened with Blackwell too. The same exact thing. They were saying you can run them at 40. So we started testing them, and they weren't really operating right. So we had to lower the minimum to 30, or the maximum to 30. So it's not that all of a sudden there's going to be no need for chillers in data centers. I mean, it would be great for the environment and for the efficiency if it was possible, but things are actually trending in the other direction. We're going to need more and more chillers. But the beautiful thing about liquid cooling is you can run it at a higher temperature than air cooling, and the chillers are higher temperature chiller than the air-cooled chillers, so there is more efficiencies to be had. Hoppers, the one before Blackwell, a lot of those were run on free cooling a lot of the time, and only in rare cases, and in Blackwell a little bit more, and in Vera Rubin it's going to be more. So I don't think he's going to retract that statement, but it wasn't exactly accurate.
Yeah, I mean, Angela, you read a lot of stuff in the news all the time about everything that happens at Nvidia, but I mean, can you, from just a technical perspective, explain why people aren't going to run their chips at 40 degrees? I mean, there's nothing sounds wrong about
No, actually, if you can run it at 45 C, which is what he said, that's 113 Fahrenheit. That'd be fantastic because, like Steven said, you could reduce the need for the chips, right? You could use a dry cooler and you could just cool with the air outside. The problem with it is, as Steven said, not in Arizona, you're not going to be able to do that 100% of the time. In most places around the world, you will not be able to do it 100% of the time. So we're not going to get away from having that for sure. But what will happen, and I like to think that Jensen was painting this, this idea of what could be. And I think that's useful because when you put out a vision of what could be and you start making small steps towards it, then it becomes a reality. And so in order for something like that to happen, as Steven mentioned, you'd have to verify all the components that are in the system to that level for reliability. You would also likely have to have a dedicated loop for that particular IT. So you'd likely I'm not an infrastructure person, maybe Steven could do this, but you'd likely have a hot loop and a cold loop because right now the facility water loop usually has multiple systems on it. So there'd need to be some architecture changes and some validation and warranties that would happen in order for that to be true. But if it could happen, it would save a lot of water and a lot of energy.
Yeah, and if you're running AI training, you could stand some disruptions because it'll just pick up from where you left off if you overeat. But if AI and AI is becoming increasingly embedded in critical business processes, data center operators are not going to take the chance of going down. A lot of data centers are being considered in the UK critical facilities, in the US critical facilities, and there's certain rules now that you can't take these chances. You need to.
It was the Chicago Metal Exchange, was it, that went down because it was a coolant distribution unit broke inside the data center, and that brought it offline for a while. I mean, I also think it's interesting because I think like the hotter you run the chip, the more it degrades. And then on the previous panel, we were discussing the role of depreciation schedules and kind of long-term chip performance. And yeah, so even like the details of how a CDU runs and the temperature it runs at influencing capital markets these days.
Well, I do think that if you're going to run it, if you're going to overclock it, when you run it hotter like that, immersion's a better solution.
Immersion's better, so okay, interesting. So, I mean, there was that conversation from Nvidia about the chillers, I think that drew a lot of headlines. I think on the electrical side of things, I mean, Haroon, you mentioned this a couple of times, that you want to move to an electrical architecture that really reduces the amount of lost power that kind of enters the data center. And I think the phrase that defines this movement is the kind of 800 volt direct current. And could you give a primer for the audience on like what that means in the context of a data center? And just give a primer on that.
So I think one of the reasons to raise the voltage from 240 or 220 or 277 single phase line to neutral, almost take it up 3 times to DC, is you're going to reduce the amount of current. And by reducing the amount of current, your bus bars, your copper bus bars can carry more power. So voltage generally can be free, but the issue with a higher voltage are the safety aspects, where people are worried about arc flash. What happens if there are shorts and this flash happens that can melt a human body in a fraction, right, of time. So it's mitigating those concerns. That's one of the big topics. But 800 volts DC also eliminates a number of power conversion stages, getting to where you can get higher efficiency, less losses, and more delivery of power. And it allows you to take those Gen AI servers straight in and mitigate those pulses that the Gen AI servers are requiring also with a similar battery or supercapacitor. And that's where this 800 volt DC architecture came from. Okay. Lower currents, higher efficiency, less number of conversion stages.
Yeah, so there's not one 800 volt DC architecture.
So I mean, this is what I was going to ask you, Steven. Can you explain the kind of the fork that's happened between what some companies want and what other companies want? Yeah,
it's interesting because the industry landed on 800 volts DC because they wanted, there was connectors and there was breakers and there was SSTs, solid state transformers, from the car industry, the automobile industry for high voltage charging. So all the safety things were in place, so they decided to do that. The first iteration of 800 volt DC is what the industry is calling sidecar. So because you want to run your AI, the accelerated compute, as one monolithic GPU, the GPUs have to be as close together as possible. The way to get the GPUs or more GPUs closer is to take the power supplies out of the server. So we're taking the power supplies out of the server and we're putting it into this thing the industry is calling a sidecar, which is sitting next to the rack. And the sidecar has the power supplies, has the capacitors, has the battery backup units and the breakers and fuses in it. So you're disaggregating all of that. You're freeing up the ability, and you're taking 800 volts from that sidecar to the GPU rack. And in NVIDIA terms, it's the NVL72s. They're going to be NVL 144s. They're eventually going to be NVL 576, which is the number of GPUs that they're going to try to stuff into these boxes.
So basically, they're just keep stuffing more stuff in.
Stuffing more and more in. But AMD has their own spec and their own version of this, which has different capacitors and different ride-through. The NVIDIA chips actually have a higher degree of disruption back onto the utility than some of the others. The AMD, Meta has a plus or minus 400 volt, 800 volt DC that they call Mont Diablo, and then Google has another one. So we have to develop 4 of those different sidecars, one for each of these different applications. But overwhelmingly, the market is NVIDIA, overwhelmingly.
Okay. So there's a lot of, from across the whole spectrum of equipment that's going to data centers, there's a lot of innovation and changes. To what extent is there any kind of bottlenecks in terms of manufacturing to kind of, obviously there's enormous demand to keep building out these data centers. Are there any bottlenecks? Are you investing in additional manufacturing capacity? Angela, I'll go to you first.
Sure, yes. Yes, to all that. We are investing in additional manufacturing. We just announced a new factory. We have 2 factories in the Dallas area. CDUs are a hot commodity. We've announced a range of CDUs. I know Schneider just made an announcement recently as well. So yeah, it's going gangbusters right now.
Yeah. And then, Haroon and Jill, to what extent are the products that you're manufacturing like commercial and being sold at scale right now? Like, what's your timeline for the next few years? I'll go to Jill first.
Yeah, so for us, we're just about to commission our first commercial scale cable winding machine that will go live this year, and that will be our first commercial scale production line. We do have one production line already up and running, but that will be sort of a broad scale commercial line. So we're busy investing exactly in that manufacturing and as well as building out our supply chain, right? We are a system, so we source components from all sorts of other vendors, and we're kind of bringing those together and then shipping them out to customers. That's top priority for 2026 for us.
When we started, we went to one of the top consulting companies in the world, and we showed them our device concept. And we said, hey, look, we got this ultra small factory to make it. And they said, not in those words, they said, hey, you're an idiot. If you get this product, you won't ever be able to keep up with the demand. So what we urge you to do is come up with a small work cell that you can expand far faster than the orders come in. So we took that advice to heart, and we have perfected a 5,000 square foot work cell in which we can make 400 megawatts a year for $2 to $3 million capex. And so you're going to get hundreds of millions of dollars of revenue from that. But when we go in there and we get a 100,000 square foot facility, we can moderate the capex of $2-3 million per work cell to speed up as the orders come in. And so we're putting in about a multi-gigawatt facility in Raleigh, North Carolina, and we're looking at a similar facility in UAE, in free trade zones, to meet the unprecedented demand. We're in negotiations for capacity reservations with some neocloud people and some other data center developers. But we're seeing a demand come. And had we not engineered the quality and the supply chain from day zero, then the wheels would be coming off. But I think it was that advice from that top consulting company to focus on supply chain and quality up front.
Am I understanding correctly then that across all the products, it's like a relatively onshored supply chain already? It's not like concentrated abroad?
I think in our case, our supply chain is multifaceted because not all the demand is going to come from the United States. A big part of it is. But we know the country of origin of every single part. And so we can shift the supply chain based upon what people want. If people want BABA compliance, we'll have a slightly amended supply chain. If the DoD, Department of Defense, wants exclusive US manufacturing, then the cost is going to be a little bit higher. But so it is for everybody else. So we have that. And then if some are agnostics to the supply chain in the rest of the world, then we can alter and compete on cost more ruthlessly.
Please join me in giving my panelists a round of applause.
Today's episode of Switched On was produced by Cam Gray with production assistance from Kamala Schelling. BloombergNEF is a service provided by Bloomberg Finance LP and its affiliates. This recording does not constitute, nor should it be construed as investment advice, investment recommendations, or a recommendation as to an investment or other strategy. BloombergNEF should not be considered as information sufficient upon which to base an investment decision. Neither Bloomberg Finance LP nor any of its affiliates makes any representation or warranty as to the accuracy or completeness of the information contained in this recording, and any liability as a result of this recording is expressly disclaimed.